Greetings, curious humans. Welcome to an exciting journey through the vast expanse of space. Today, we embark on a captivating exploration of the planet that orbits closest to our fiery sun, Mercury. From ancient civilizations naming it after their mythological gods to the modern age of space exploration, Mercury has captivated our imaginations. Today, we'll unlock the secrets held within its rugged surface, its turbulent history, and its peculiar orbit. Over the years, humanity has sent spacecraft to unveil the mysteries of Mercury. Join us as we traverse through time and witness the remarkable achievements of missions like Mariner 10 and Messenger, which have brought us closer to understanding this mesmerizing planet. We'll discover how Messenger revolutionized our knowledge, revealing Mercury's hidden wonders and unveiling surprises that challenged everything we thought we knew. But our quest doesn't end there. We'll also glimpse into the future with the ambitious Bepi-Colombo mission, set to push the boundaries of our understanding even further. Mercury, a planet of extremes, with blistering temperatures and a thin atmosphere, holds secrets that have fascinated astronomers for generations. Its geological features, magnetic field, and intriguing orbit provide endless opportunities for exploration and discovery. So, fasten your seatbelts and get ready to embark on an extraordinary voyage to the innermost planet of our solar system. Join us as we unlock the secrets of Mercury and delve into the wonders that await us in this captivating world. Let's embark on this cosmic journey together, fueled by our insatiable curiosity, as we uncover the mysteries of Mercury, a world that continues to ignite our passion for exploration and expand our understanding of the universe. Mercury is the smallest planet in our solar system and the closest one to the Sun. It has a heavily cratered surface and a thin atmosphere called an exosphere. Despite its small size, Mercury has a similar surface gravity to Mars. The planet has a dynamic magnetic field, about 1% as strong as Earth's, and no natural satellites. The current understanding suggests that Mercury has a solid silicate crust and mantle, followed by a solid outer core, a liquid core layer, and a solid inner core. Due to its lack of atmosphere, Mercury experiences extreme temperature changes, ranging from -173 degrees Celsius -280 degrees Fahrenheit at night to 427 degrees Celsius 800 degrees Fahrenheit during sunlight at the equator. However, at the poles, there are large reservoirs of water ice that are never exposed to direct sunlight. Mercury's proximity to the Sun means that sunlight on its surface is much more intense compared to Earth, ranging from 4.59 to 10.61 times the solar constant. It has a unique spin-orbit resonance, rotating on its axis 3 times for every 2 revolutions around the Sun. This results in a long Mercurian solar day of 176 Earth days, while its orbit takes only 88 Earth days. Like Venus, Mercury can only be seen in Earth's sky as a morning star or an evening star due to its position within Earth's orbit. It is named after the Roman god Mercurius, associated with commerce, communication, and the messenger of the gods. Mercury is challenging to reach from Earth due to the significant change in spacecraft velocity required. Only 2 spacecraft, Mariner 10 and Messenger, have visited Mercury so far. Mariner 10 flew by in 1974 and 1975, while Messenger orbited the planet over 4,000 times between 2004 and 2015. The Bepi-Colombo spacecraft is expected to arrive at Mercury in 2025 and deploy 2 orbiters for further exploration. Mercury, also known as Stilben and Hermes in ancient Greek, and named after the Roman messenger god Mercury, is the smallest planet in the solar system. It has a rocky composition similar to Earth, consisting of approximately 70% metallic and 30% silicate materials. Mercury's density is the second highest in the solar system, indicating a large and iron-rich core. Its core makes up about 57% of its volume, compared to 17% for Earth. The planet's internal structure includes a solid silicate crust and mantle, an iron sulfide outer core layer, a liquid core layer, and a solid inner core. The thickness of the mantle crust layer is estimated to be 420 kilometers, with the crust itself about 35 kilometers thick, although some models suggest it could be as thin as 26 kilometers. Mercury's surface features numerous narrow ridges, believed to have formed as the core and mantle cooled and contracted while the crust was already solidified. The high iron content of Mercury's core is distinct from other major planets in the solar system. One widely accepted theory suggests that Mercury originally had a metal-silicate ratio similar to common chondrite meteorites and experienced a massive impact that stripped away much of its original crust and mantle. Another hypothesis proposes that Mercury formed from the solar nebula before the Sun's energy output stabilized, leading to the vaporization of surface rock and the loss of lighter particles due to drag from the solar nebula. Observations by the Messenger spacecraft, which orbited Mercury from 2004 to 2015, indicated higher-than-expected levels of potassium and sulfur on the surface. This finding challenges the hypothesis of a giant impact and vaporization, as those events would have driven off such elements due to extreme heat. The Bepi-Colombo mission, set to arrive at Mercury in 2025, aims to gather further data and observations to test these hypotheses. In summary, Mercury is a small rocky planet with a significant iron-rich core. Its internal structure includes a silicate crust, mantle, and various core layers. The planet's composition and surface features provide insights into its formation and evolutionary history, which are being further explored through space missions like Messenger and Bepi-Colombo. Mercury's surface is similar to the Moon's, with extensive plains and heavy cratering, indicating geological inactivity for billions of years. It is more heterogeneous than Mars or the Moon, with various features such as ridges, mountains, plains, escarpments, and valleys. The planet's mantle is chemically diverse, suggesting a magma ocean phase early in its history. The surface composition includes iron porphyroxene and olivine, sodium-rich plagioclase, and minerals with mixed magnesium, calcium, and iron sulfide. Carbon, likely in the form of graphite, is also present in less reflective regions. Features on Mercury are named after deceased individuals, including craters named after artists and ridges named after scientists. The planet experienced intense crater formation due to impacts from comets and asteroids during its formation and the late heavy bombardment period. The impacts were facilitated by the lack of an atmosphere. Volcanic activity occurred, filling basins with magma and creating smooth plains. The largest known crater is Caloris Planitia, which caused lava eruptions and formed a concentric mountainous ring. The antipode of Caloris Basin features unusual hilly terrain known as the Weird Terrain. Mercury has 46 identified impact basins, and its surface has undergone space weathering processes. There are two types of plains, older intercrater plains and younger smooth plains, likely of volcanic origin. The surface also exhibits compression folds and thrust faults, with prominent lobate scarps. Mercury's surface has evidence of pyroclastic activity and compound volcanoes. Mercury has extreme surface temperatures ranging from 100 to 700 K, minus 173 to 427 degrees Celsius, minus 280 to 800 degrees Fahrenheit. The temperature never exceeds 180 K at the poles due to the absence of an atmosphere and a steep temperature gradient between the equator and poles. The sunlight intensity on Mercury's surface is significantly higher than the solar constant. Despite the high temperatures, observations suggest the presence of ice in deep craters at the poles that are permanently shadowed from direct sunlight. The presence of ice is supported by radar reflections, and estimates suggest the existence of 100 trillion to 1 quadrillion kilograms of ice on Mercury's surface. The origin of the ice is uncertain but could be from outgassing or impacts by comets. Mercury lacks a significant atmosphere and has a tenuous surface-bounded exosphere containing various elements such as hydrogen, helium, oxygen, sodium, calcium, and potassium. The exosphere is continuously replenished and lost from various sources, including the solar wind and radioactive decay. Water vapor is also present, likely originating from comets, sputtering, and sublimation from water ice in polar craters. Sodium, Potassium, calcium, and other elements are thought to result from vaporization of surface rock by micrometeorite impacts. Mercury's surface is not suitable for Earth-like life due to its extreme temperatures, lack of atmosphere, and high solar radiation. However, some subsurface regions may have been habitable in the past, potentially supporting primitive microorganisms. Mercury possesses a significant and apparently global magnetic field, despite its small size and slow rotation. Measurements from the Mariner 10 and Messenger probes have indicated that Mercury's magnetic field is about 1.1% the strength of Earth's and is dipolar in nature. The magnetic field is stable and generated by a dynamo effect, similar to Earth's magnetic field, resulting from the circulation of the planet's iron-rich liquid core. The high orbital eccentricity of Mercury, combined with strong tidal heating effects, helps maintain the liquid state of the core necessary for the dynamo effect. Mercury's magnetic field is strong enough to create a magnetosphere, deflecting the solar wind around the planet. Although small compared to Earth's magnetosphere, it is capable of trapping solar wind plasma, contributing to space weathering of the planet's surface. The magnetosphere exhibits dynamic characteristics, with bursts of energetic particles and the presence of twisted magnetic flux tubes called flux transfer events, which create open windows in the magnetic shield. These windows allow the solar wind to directly impact Mercury's surface via magnetic reconnection. The rate of reconnection is higher at Mercury compared to Earth, although proximity to the Sun accounts for only a portion of the observed difference. Mercury has the most eccentric orbit among all the planets in the solar system, with an eccentricity of 0.21. Its distance from the Sun ranges from 46 million to 70 million kilometers, 29 million to 43 million miles, and it takes approximately 87.969 Earth days to complete one orbit. The eccentricity of its orbit results in varying distances from the Sun, causing tidal bulges on Mercury's surface that are about 17 times stronger than the moon's on Earth. Additionally, Mercury has a 3-to-2 spin orbit resonance, meaning that a single solar day on Mercury lasts exactly 2 Mercury years, or about 176 Earth days. Mercury's orbit is inclined by 7 degrees to the plane of Earth's orbit, making it the largest inclination among all known solar planets. Transits of Mercury across the face of the Sun can only occur when the planet is crossing the plane of the ecliptic and lies between Earth and the Sun. These transits happen approximately every 7 years on average. The axial tilt of Mercury is nearly zero, with a measured value as low as 0.027 degrees. This means that an observer at Mercury's poles would see the center of the Sun never rise more than 2.1 arc-minutes above the horizon. Due to its varying distance from the Sun and its 3-to-2 spin orbit resonance, there are points on Mercury's surface where the Sun appears to reverse its motion, creating retrograde apparent motion. This results in prolonged exposure to the Sun at its brightest and makes these points the hottest places on Mercury. Mercury attains inferior conjunction, nearest approach to Earth, every 116 Earth days on average, with a range of 105 to 129 days due to its eccentric orbit. The period of retrograde motion as seen from Earth can vary from 8 to 15 days on either side of inferior conjunction. Mercury is often the closest planet to Earth on average, and it is also the closest planet to each of the other planets in the solar system when considering average distances. The longitude convention for Mercury was initially challenging to establish due to the lack of visibility in the area where the zero meridian was intended to be. Therefore, a small crater called Huncal, located further west, was chosen as the reference point for measuring longitude. The center of Huncal defines the 20 degrees west meridian. There are 2 convention options for measuring longitudes on Mercury, a west-positive convention suggested by the International Astronomical Union and an east-positive convention used by the Messenger project. Mercury's rotational motion was initially believed to be synchronously tidally locked with the Sun, similar to the Moon's relationship with Earth. However, radar observations in 1965 revealed that Mercury has a 3-to-2 spin orbit resonance, meaning it rotates 3 times for every 2 revolutions around the Sun. This resonance is stabilized by the eccentricity of Mercury's orbit, which causes the tidal force to exert a maximum effect at perihelion, resulting in the resonance locking the planet's rotation. Mercury's rotation period is nearly half of its synodic period with respect to Earth, which is why it appeared to show the same face whenever it was best placed for observation. A solar day on Mercury, which lasts about 176 Earth days, is significantly longer than its sidereal day, the period of rotation, which lasts about 58.7 Earth days. Numerical simulations indicate that Mercury's orbital eccentricity varies chaotically over millions of years due to gravitational perturbations from other planets. This eccentricity plays a role in the 3-to-2 spin orbit resonance of Mercury. However, accurate modeling based on tidal response suggests that Mercury was captured into this resonance early in its history, within 20 million years after its formation. In the distant future, there is a possibility that a secular orbital resonant perihelion interaction with Jupiter may increase Mercury's eccentricity to the point of destabilization. If that happens, Mercury could potentially fall into the Sun, collide with Venus, be ejected from the solar system, or cause disruption in the inner solar system. The observed precession of Mercury's perihelion is explained by Albert Einstein's general theory of relativity. The effect is small but measurable, with a precession of approximately 42.98 arcseconds per century. This deviation from Newtonian predictions confirms the accuracy of Einstein's theory and requires millions of years for a full excess turn. Overall, Mercury's longitude convention, spin-orbit resonance, eccentric orbit, and precession provide intriguing insights into the dynamics and characteristics of this fascinating planet. Mercury's apparent magnitude, which is a measure of its brightness as seen from Earth, varies depending on its position in relation to the Sun. During superior conjunction, when Mercury is on the opposite side of the Sun from Earth, its apparent magnitude can reach as bright as -2.48, making it brighter than Sirius, the brightest star in the night sky. On the other hand, during inferior conjunction, when Mercury is between Earth and the Sun, its apparent magnitude can drop as low as +7.25, which is below the limit of naked eye visibility. The mean apparent magnitude of Mercury is 0.23, but it has the largest standard deviation of 1.78 among all the planets. At superior conjunction, the mean apparent magnitude is -1.89, while at inferior conjunction, it is +5.93. The variation in Mercury's apparent magnitude is due to its changing distance from Earth and the varying amount of sunlight reflecting off its surface. Observing Mercury can be challenging because it is often lost in the sun's glare. It can only be observed during a brief period of either morning or evening twilight. However, under certain circumstances, such as when its position is known, Mercury can be observed with a telescope in daylight. When it is near superior conjunction and higher in the sky, it is less affected by atmospheric effects and can be viewed safely with proper precautions. Mercury, like the Moon and Venus, exhibits phases as seen from Earth. It appears new at inferior conjunction and full at superior conjunction. However, during these conjunctions, Mercury is obscured by the Sun and becomes invisible, except during a transit when it passes in front of the Sun. Mercury is technically brightest when it is at a full phase as seen from Earth. Although it is farthest from Earth at that point, the larger illuminated area compensates for the increased distance. However, observing Mercury at its full phase is challenging due to its proximity to the Sun. It is best observed at the first and last quarter phases when it is at its greatest elongation east or west of the Sun. During these times, Mercury can be seen rising before sunrise or setting after sunset. Mercury is more easily visible from the southern hemisphere compared to the northern hemisphere. Its maximum elongation occurs during early autumn in the southern hemisphere, allowing it to rise before sunrise or set after sunset. In the northern hemisphere, the conditions for visibility are less favorable. Observing Mercury during daylight hours when it is at its greatest elongation is another method, especially when using telescopes with appropriate precautions. However, the Sun must be obstructed from sight to avoid the risk of eye damage. Ground-based telescope observations of Mercury reveal only a partially illuminated disk with limited detail. The Mariner 10 spacecraft, which visited Mercury in 1974 to 1975, mapped approximately 45% of its surface. The Messenger spacecraft, after multiple flybys, entered orbit around Mercury in 2011 to study and map the rest of the planet. The Hubble Space Telescope cannot observe Mercury due to safety procedures that prevent it from pointing too close to the Sun. Mercury's orbit and phenomena exhibit a 7-year cycle, where its sequence of events approximately repeats itself after 7 years, with a slight shift of 7 days. The earliest recorded observations of Mercury date back to the Mul.Appen tablets, believed to have been made by an Assyrian astronomer around the 14th century BC. Babylonian records from the first millennium BC refer to Mercury as Nabu and associate it with the messenger to the gods in their mythology. Ptolemy, a Greco-Egyptian astronomer, speculated on the possibility of planetary transits across the Sun but concluded that they were either too small to see or too infrequent. In ancient China, Mercury was known as the hour star and associated with the direction north and the phase of water. Hindu mythology referred to Mercury as Buddha, presiding over Wednesday. During medieval Islamic astronomy, observations of Mercury were made by astronomers like al-Zarqali, who described its geocentric orbit as oval. Ibn Bajjah observed what may have been a transit of Mercury or Venus, and these reports were later considered observations of sunspots. In India, Nilkantha Somyaji developed a partially heliocentric model with Mercury orbiting the Sun, similar to Tycho Brahe's Tychonic system. The first telescopic observations of Mercury were made by Thomas Harriot and Galileo in 1610. Pierre Gassendi observed the first transit of Mercury across the Sun in 1631, and Giovanni Zuppi discovered its orbital phases. These observations confirmed that Mercury orbits the Sun. In 1737, John Bevis observed the occultation of Mercury by Venus, the only such event historically observed. The next occultation will occur on December 3, 2133. Early observations of Mercury's surface by Johann Schroeder, Friedrich Bessel, and Giovanni Schiaparelli provided insights into its features and rotation period. The first radar observations of Mercury were made by Soviet and American scientists in the 1960s, revealing its rotation period and surprising magnetic field. Mariner 10, launched by NASA in 1974, made the first close-up observations of Mercury and provided valuable data on its surface, magnetic field, and atmosphere. Messenger, launched in 2004, further explored Mercury and addressed key scientific questions. It orbited Mercury from 2011 to 2015, gathering detailed data before its planned impact on the planet's surface. The Bepi-Colombo mission, a joint effort by the European Space Agency and the Japanese Space Agency, was launched in 2018 and is expected to reach Mercury in 2025. It consists of 2 probes, one for mapping the planet and the other for studying its magnetosphere. Bepi-Colombo aims to provide further insights into Mercury's geological history, magnetic field, core structure, polar ice, and tenuous atmosphere. As we conclude our fascinating exploration of the mesmerizing planet Mercury, we hope this journey has ignited your curiosity and expanded your understanding of our extraordinary universe. Mercury, with its scorching temperatures and peculiar characteristics, continues to challenge our knowledge and inspire scientific exploration. From its elusive magnetic field to its crater-filled surface, this planet has left us in awe of its complexity. But our cosmic voyage doesn't end here. The vastness of space awaits, with countless celestial marvels yet to be discovered. Let the exploration of Mercury be a catalyst for your own explorations, both within the realm of science and in your personal pursuit of knowledge. We encourage you to keep seeking, keep questioning, and keep looking up. The mysteries of the universe are vast, and each discovery brings us closer to unlocking the secrets of our existence. Thank you for joining us on this captivating expedition. Remember, the universe is a tapestry of wonders, waiting to be unraveled. Continue to gaze at the night sky with wonderment, and let the mysteries of the cosmos guide your journey. Until we embark on our next adventure together, keep exploring, keep dreaming, and keep embracing the awe-inspiring beauty of our cosmos. Safe travels, fellow adventurers. See you among the stars. Remember, the sky is not the limit, it is only the beginning.